How we doing, you guys? This is a very exciting day for you. We are going to learn how to do the shortcut on how to find derivatives. So instead of using that really annoying, super long, confusing, tricky limit where you have to plug in x plus h and all that garbage, there happens to be a shortcut. Now remember, it is important that you understand how to come up with the derivatives mathematically. However, there is a shortcut that I'm going to show you that can save you a lot of time. And this is definitely a skill that you're going to want to have on the AP. Okay, first of all, let's copy down a couple things. The derivative of a constant function is always 0. Here's the reason for that. Do you remember what a constant function looks like on a graph? It's like a horizontal line, correct? And so if we want to know what the derivative of that horizontal line is, can you imagine a roller coaster going horizontally like this? Not very scary, my kind of roller coaster, right? But at any point on that horizontal trajectory of the roller coaster, the slope is 0. Would you agree? That's why the derivative of any constant function is always 0. That means the slope at this point of this function is 0. Okay, so that is why. In your group work, what I challenged you in your groups to do is try to figure out what the pattern is or how to come up with the shortcut for finding the derivative of a function. So here's our original function. Notice the notation here. Here's the derivative. Remember, that's the f prime of x. So here's the original function, here's the derivative. Here's the original function, here's the derivative. Now remember that you could plug in x plus h right here and right here, and then subtract the original function and then divide by h and then take the limit as h approaches 0. You could do that for all of these equations and end up with this. You learned how to do that the very first day of this chapter. Flip back to the very first page of your notes. That's what we taught you. Okay, but here, some things that hopefully you're starting to notice is that the degree of this function is 2. The degree of the derivative is 1. Notice how the exponent on the x decreases by 1 every time. This exponent went from 3 to 2. This exponent went from 4 to 3. This exponent went from a 1 exponent to a 0 exponent, meaning there's no x left. Okay, so how about the coefficients? That's weird. Let me look at like this one first. We started with a coefficient of 1 and we ended up with a coefficient of 4. I wonder how that happened. This one we started with a coefficient of 2 and we ended up with a coefficient of 6. Okay, well, if you're looking ahead at like the formula that I have down here, what you do is you take this exponent and you multiply it by the coefficient here. That's why 3 times 2 is 6. And notice how this exponent decreased by 1. Same thing over here. You bring this exponent down in front and multiply it by the 1 that's already there and gives you a 2. And then decrease the exponent, so there's just a 1 exponent here. And then what's the exponent on this x? It's a 1, so bring it down. There's where the 1 is, and then decrease this exponent. So this exponent goes from a 1 to a 0. And x to the 0 you don't write right here. And the derivative of a constant function is 0, so I don't have a plus 0 at the end of this one. Okay, so shortcut again. 3 times 2 is 6, x to the second, decrease the exponent by 1. And then let's look at this term. The 2 comes down in front, that's why it's negative 2. Keep the x and then decrease the exponent, so this is technically an x to the first. This one, bring the 4 down in front and decrease the exponent, 4x to the third. This is the most simple one that we will look at. And then same thing here. So this x has a 1 exponent right here, and when you multiply it by the 2, you just get 2. And then keep the x to the 0 power, which means there's just a 1 here. There's no x at all. Okay, so that is the shortcut. If you have a whole number multiplied by x to a certain exponent, you multiply the a and the n, that's why we have a and n right here, and then the exponent, the x stays, but the exponent decreases by 1, and that is it. Let's dive into some examples, and let me show you how simple these are. So be really careful with your notation here. This is the original function. I want to find the derivative, so f prime of x. Equals, I'm going to multiply the 3 by the negative 4 that's already there, and that gives me negative 12. Keep the x, but decrease the exponent by 1. This is a 1 exponent on this 6 here, or on this x, so I'm going to take this 1 and multiply it by negative 6, which gives me negative 6. X to the 0 power. Oh, okay, so I don't even need actually to write x to the 0. It's just a whole number. Okay, this is the derivative. And that is super exciting because that's the same exact thing I would get if I would evaluate this limit. The limit as h approaches 0, f of x plus h minus f of x all over h. Remember how to do that? Where you plug in the x plus h to this x and cube it. Oh my god, that would suck. And then plug in x plus h here, and then subtract the entire function, and then divide by h, simplify, sub in 0. Here's the shortcut. Much, much faster. Let's try some more. Here's a trick for you. I would like to rewrite this instead of with a radical. I would like to change it to original function x to the 1/3. Remember how fraction exponents mean radicals? And so now what I can do is I can use my power rule, like the exponent rule, to figure out what the derivative is. So I'm going to bring down the 1/3, keep the x, and I'm going to decrease the exponent by 1. What's 1/3 minus 1? Happens to be negative 2/3. You have to be okay with fractions there. What I did is 1/3 minus 1. That means 1/3 minus 3/3, which gives me negative 2/3. That's the exponent after you decrease it by 1. So it gets a little bit tricky with fractions. Okay, just know that this is the same exact answer as 1/3. There's an x. There's an x here with a 2/3. Remember how a negative exponent does not make your answer negative. A negative exponent means whatever the exponent is on goes into the denominator. So these are equivalent. These two things are equal. It's the same exact way of writing it. A third way of writing it is 1/3. Let's put the x back in a radical. It happens to be a cube root. That's all the same thing. This is also equivalent. So keep in mind, multiple choice tests, you might have to choose whatever the right answer is. Technically, a negative exponent is not considered simplified, so let's drop it down into the bottom. But if you want to leave your answer like this, it's fine. It means the same exact thing as a radical. Okay, let's try a couple more. 3/x. I am going to change this. I'm just going to rewrite it a little bit. This means 3 times x to the negative 1. Would you agree? That means that the negative 1 exponent is on the x and the x only, so the 3 stays and the x ends up in the denominator. This is just an easier way to rewrite. I'm going to write rewrite. I'm not changing it or taking the derivative yet. I'm just rewriting it so that I can use my exponent rule. This negative 1 exponent is going to multiply by the 3, and then this number is going to decrease by 1. So now I'm ready to take the derivative. Notice how I'm always writing f prime of x, so I'm keeping straight what's my original function and then what's the derivative. Okay, so I'm going to bring the negative 1 exponent down. That's going to multiply by the 3 and give me 3. And be careful, when you decrease negative 1 by 1, you get negative 2, you guys. It's not 0. You're decreasing the exponent. So this is another equivalent way of keeping the 3 on top and making it x squared in the bottom. So the exponent is only on the x. The negative 3 stays where it is, okay? These are equivalent. This one is a better answer because a negative exponent is not considered fully simplified. All right, what's next? Ooh, some more fractions, okay. F prime of x equals, I'm gonna bring the 5/3 down, and I'm gonna decrease the exponent by 1. So it's really subtracting 3/3, and that's how I'm gonna get 2/3. That's for the first term. Second thing I'm going to do is I'm going to bring this exponent down in front and multiply it by the 6. Well, what happens to be 6 times 2/3? It's 12/3 or 4. T to the, and again, when I subtract 3/3, I'm decreasing the exponent by 1. That gives me negative 1/3. Okay, I do have a fraction exponent that's a negative, so that's considered not fully simplified, so I can simplify this a little bit. The 2/3 is fine because it's positive, but I'm going to drop this t down into the denominator because it had a negative exponent on it. Now remember your Algebra 2 skills. This exponent only goes with the t, the 4 stays in the top. Okay, so here is our final answer for the derivative for that one. Let's do just a couple more. I'm going to rewrite this because I'm going to get it out of radical form. So my original function is the same thing as saying x to the 3/5. And so now that it's in a fraction exponent, I'm able to implement my rule. So the derivative, I'm going to bring the 3/5 down in front, and decrease the exponent by 1. So subtract 5/5 gives me negative 2/5, which I need to simplify a little bit more. That means 2/5 for the x in the denominator. There we go. Okay, let's try this one. This one looks a little bit crazy. This has a radical in it, so I'm going to change that to a fraction exponent so I can get rid of the radical. I'm also going to bring this t to the 4th up as a negative 4th exponent, so I'm just going to rewrite this just so that I can make it a little bit easier to use my formula. So 5/6 t to the 18th plus t to the 2/7 minus 8/3 t to the negative 4. See what happened there is I just brought the t up, so I put a negative exponent on it. This, if I were to simplify it, would just drop down into t to the positive 4th. But I want all my t's to have exponents on them and not be like fractions and radicals so that I can bring my exponents down in front and multiply. So now what I'm going to do is find the derivative. H prime of t equals, first thing I'm doing is taking the 18 and multiplying it by 5/6. 18/6 reduces to 3. 3 times 5 is 15. And decrease the exponent of 18 by 1, so the exponent becomes 17. Now let's look at the second term. I'm going to bring this 2/7 down and multiply by the 1 that's in front of there. So it's just 2/7 t to the negative 5/7. Yes, I'll drop that into the bottom in just a second, but remember you have to decrease the exponent by 1. That's how I got negative 5/7. Got to be okay with doing some fraction work here. And then the last part, what I'm going to do is I'm going to bring this negative 4 and I'm going to multiply it by negative 8/3, which gives me positive 32/3. T to the, how do you decrease negative 4 by 1? You make it negative 5. Be careful with your exponent rules, you guys. Okay, now all I have to do is drop these t's into the denominator since they have negative exponents. So h prime of t totally simplified is 15t to the 17th plus 2/7t to the 5/7 plus 32/3t to the 5th. And that is my final answer, you guys. Okay, that's enough for now. We will pause and we'll finish the rest of the notes in class. Just make sure you remember how to do that exponent rule, and you're welcome for showing you a shortcut, you guys. Remind me to tell you a funny story about when I was in college and I was in calculus and we were learning the limit and I already knew the shortcut and I blew somebody's mind, okay? Remind me to tell you about that. All right, I will see you guys tomorrow. Have a good night.